Assume the length of the string is some 2 meters and the mass of this particle or ball assume is 4 kg. Okay. Now, if you leave the ball there itself, it is going to stay like that because weight and tension will balance. Nothing will happen. It will be in equilibrium if the string is strong enough. Rishi, tell me what will happen if you strike the ball and give it some velocity to the right?
Here it will go towards the right and then oscillate.
Ha. Depending on how much velocity you give or how hard you strike it, it will swing to greater and greater extents. Good. So you have to find out how much velocity the ball must be imparted such that it swings, such that the string rotates by a maximum of 37 degrees, or let's take 53 degrees. So it should rotate by 53 degrees before the bob or the ball stops. So we
Sir,
want it.
so
Wait.
the max
Wait. So we want it to swing by 53 degrees. So how much initial speed should the ball be given such that the string rotates by 53 degrees before stopping? Yeah, what were you asking?
sir, I was asking that like when the bob goes towards right, the
Hmm.
53 should be the maximum angle it can do, and
Maximum
then
angle.
it
Yes. Yes. So listen, like analyze the situation first. Basically, this is a case where an object is moving from one place to another. So some movement is there, means some change in arrangement is there. And you are asked to find out the velocity at one position. And you know that at the other point, like when the string rotates by 53 degrees, the bob comes to rest. So you know the velocity at one position. You need to find out the velocity at some other position. And an object is moving from one point to another. Now, last class we discussed 3 different ideas that can be used to solve problems like this. Can you tell me all the 3 ideas? Like if you know from where to where an object has gone and you are asked to find out one of its velocities, either the initial or the final, what are the methods that we can use? Tell me equations we learnt involving displacement, initial velocities and final velocities. Like in what all concepts are these connected?
Sir, V square minus U square is equals to S.
Okay, that's one way you can attempt such questions. But this comes with a condition. We know that the condition is that acceleration should be constant. We'll see. Next, what else can be used to solve problems like this?
Conservation of linear momentum.
Linear momentum.
Sorry.
Linear momentum conservation you will do in cases where motion of one object disturbs the motion of another object. Here it's just one object. We just need to know how far it goes. Okay, so linear momentum conservation is not applicable here. What other ideas can we use? Okay. At least like think of the name of the chapter. No? Think of the name of the chapter. Based on that, you'll get some ideas.
sir, the work energy theorem.
Work kinetic energy theorem. Now, work includes displacement, kind of, right? So you can write work done by all forces or the total work done is equal to change in kinetic energy. And change in kinetic energy will include final velocity and initial velocity, final speed, initial speed. So this is also a way to solve. And work energy theorem doesn't have any conditions. You just need to include work done by all forces. Then you can use it in any case. What other methods can we use? There is another method also which can be used. What is the concept we are now working on?
Is it potential energy initial plus kinetic energy initial is
You
equal to
call it mechanical energy conservation. Okay.
yeah.
Fine. So you may use that also. Ui plus ki is equal to uf plus kf. Fine. But mechanical energy conservation also comes with a condition. Condition should be satisfied, only then you can apply. Right. One of you tell me, can we use equations of kinematics in this case? As the bob ascends from, let's name these positions as A and B, from A to B, will the acceleration be constant? See, you need to check if acceleration is constant or not. Acceleration is given by forces. So think of what forces act on it and whether those forces are constant. Rishi, tell me, as the bob moves from A to B, what all forces act on it?
Sir, weight,
Okay,
then tension,
okay,
and
that's all. Okay.
yeah, sir, that's
Weight is a constant force or variable force?
constant.
Constant. What about tension in this case? Is it constant or variable?
Constant. It's constant.
It
No,
is
like
variable. It is
oh,
definitely
okay.
variable. Okay. Here, tension will be acting this way. At some instant in between, it will be acting like this. At this position, it will be acting like this. So at different instants, it's in different directions. Force is a vector quantity. Even if direction is changing, it means the force is changing. Now, one force is constant, but the other force is changing. So the net force will be variable. Acceleration will be variable. You must not use equations of kinematics in this case. Now, if you all remember, we had discussed equations of kinematics with speed, tangential acceleration. Okay, when like in circular motion, we had talked about all that. Now here you can think about that also. Maybe those equations of kinematics are applicable. We'll see. At any instant, okay, let's consider a random instant in between. Let's say the bob is here. When the bob is here, the forces acting on it, if you visualize, one is its weight. Weight will be acting this way, mg. The other is tension. Tension acts along the orange arrow. Okay. In the tangential direction, if you see, okay, tangent is this. Along the tangential direction, tension won't have any component because tension acts along the radius now. But mg will have a component. And mg is acting in the vertical direction, always acts in the vertical direction. Let me draw it properly. Mg acts like this. At that moment, if you visualize the tangent makes a random angle like this. The angle between weight and tangent is not 90 degrees. So mg will have a component in the opposite direction to the velocity of the ball. That's why the ball slows down. Okay. And that angle will keep on varying as the ball moves forward. Like at some other instant, if you visualize, mg continues to be in the vertical direction, but the tangent changes its direction, changes its orientation. So angle will change. And if angle is changing, the component of mg along the tangential direction will keep changing. Therefore, as this ball swings from A to B, the tangential acceleration is not constant because the component of gravity along the tangent will keep changing. Okay, so you can't apply equations of kinematics with speed and tangential acceleration also. That also cannot be done in this case. Fine. Next is work kinetic energy theorem. This can definitely be used. There are no conditions, but you should know work done by all forces. Okay. Now we know that as the ball swings from A to B, there are two forces acting on it, weight and tension. Can one of you tell me how to calculate work done by weight? Weight is a constant force or a variable force?
Sir, constant.
Constant force. How do you calculate work done by constant forces?
F dot S cos theta.
Dot annaka malla cos theta undadu. Okay, it is F dot S or Fs cos theta. Okay, fine. So basically what you need is force multiplied with displacement in the direction of the force. Remember, calculation of weight is easy to do. Not weight, sorry. Calculation of work done by weight is very easy to do. Weight always acts in the downward direction, no? So you just need to look for displacement in the downward direction. Now this ball is actually ascending. Even if it ascends, the component of displacement in the vertical direction is what matters. So you need to know how much this is. Let's call this as h for now. Okay. You need to calculate that height. Can any of you tell me how to do that? We know the length of the string. We know by what angle it is swinging. So some geometry should be used to calculate that height. Geometry or trigonometry. So can one of you tell me an idea? Let's visualize that part separately if you want. The length of the string is given 2 meters. And it swings by 53 degrees to some position like this. This length is also 2 meters only. It's the same string. And what we need is this height. How to calculate that?
Cos.
Okay. See, you see a right angle triangle forming here. You have to make use of that. Basically, the idea is that that height is the total length 2 meters minus this length. Let's call this as y. So h, the height that we are looking for, becomes the total length minus that length y. Okay, Pawan and Rishi, is this clear?
Yes, sir.
Okay. Now y can be calculated by using that right angle triangle, 2 cos 53. Okay, and L is 2 meters. So h becomes 2 minus 2 cos 53. Cos 53 is 3 by 5. So 2 minus 6 by 5, that is 10 by 5, 10 minus 6 by 4 by 5 meters is the height by which it rises. Now, why did we calculate this height? Because that is the displacement parallel to mg. But mg acts downwards, height h is upwards, it is ascending. Therefore, the work done by weight becomes, see, you can always calculate work done by weight like this, mg into delta h, okay, or minus mg into delta h. If height is increasing, work done by weight will be negative. If height is decreasing, if the object is coming down, work done by weight will be positive. Okay. So we can do it like this. mg here 4 into 10, 40. And height we just found out is 4 by 5 meters upwards. So minus 40 into 4 by 5. 540 is 8, 84 is 32. So minus 32 joules is the work done by weight. Okay, one part is done. We are trying to apply work energy theorem to calculate that initial velocity. Next thing is work done by tension. Okay. Rishi, you tell me, as the bob moves from A to B, how much will be the work done by tension? Is there a way to calculate it? Work done by tension as the bob swings from A to B.
Sir, will be different, so I'm not sure, sir.
Okay. See, you need to revise a little bit. Last class also we discussed. Last class we discussed the case of bob coming down. Do you remember what was the work done by tension in that case and why?
Sir, it was integral of t dot t
Tension is a
yeah.
variable force, so we'll use integral T dot ds. And what was the answer?
Answer was velocity was root 2 GL.
Not that answer. Work done by tension. What was the answer for that? Okay, Pawan, you tell. Will tension do any work in this case? If yes, how to calculate?
Sir, work done by tension equals 0.
Why will it be 0?
Sir, అంటే displacement ఇంకా tension 90 degrees make చేస్తాయి.
Okay. Tension and displacement are perpendicular to each other at any instant. Therefore, the work done by tension will be 0 in this case. So integral T dot ds and dot product between perpendicular vectors is 0. Okay. So there were two forces acting. We calculated work done by both the forces. Then we are now in a position to apply the work kinetic energy theorem. Therefore, total work done, what will it be? Work done by weight was how much? Minus 32 joules. Plus work done by tension is 0. Should be equal to change in kinetic energy. Half m v square. When the bob swings by 53 degrees, it has to stop. Okay, we don't want it to go beyond that. So half m v square minus u square. That's all. You can get u from there. So 4, this is 2 times 32 and 2 is 16. So minus 16 is equal to minus u square. That means u square is 16. So u becomes 4 meters per second. If you give the bob that much speed at the bottommost position, the string will rotate by 53 degrees maximum. Okay, we solved this using work kinetic energy theorem. There is another way also to solve, the last one, mechanical energy conservation. Pawan, tell me the condition for mechanical energy conservation.
Work done by external forces must be equal to 0.
External force. That's what question. Tell properly. Conservation of mechanical energy.
Sorry, work done by non-conservative forces.
Should be 0. Okay. What are the two forces acting on this bob as it moves from A to B?
Gravitation and tension.
Weight and tension. Which of them is doing work?
Mass. Weight.
Okay. Is weight a conservative force or a non-conservative force?
Conservative force.
Gravity, conservative. So the only force doing work on it is a conservative force. So there's no question of non-conservative forces doing work in this case. Therefore, mechanical energy conservation is also applicable. Let us try to solve it that way. I'll copy the diagram. Yusuf, good evening. You just joined. We were only discussing this problem. Okay. So how do we apply mechanical energy conservation? Initial potential energy plus kinetic energy is equal to final potential energy plus kinetic energy. Okay. Now the only conservative force acting here is gravity. So you'll only have to consider gravitational potential energy. Springs are not involved, so need not worry about that. One of you tell me, how do we assign gravitational potential energy? What is the formula? How do we write initial and final gravitational potential energies?
Sure, mg h2 minus h.
mg h2 minus h1 gives you the change. Okay, so
Yes,
initial
yes.
can be taken as mg h1, final can be taken as mg h2. Okay, but we don't know where the ground is. So we don't know what is the initial height of the bob and the exact final height of the bob. Then what do we do? See, you need to keep revising. Basically, to calculate gravitational potential energy, you can assume any level to be the zero height level. Nothing wrong in that. Okay, so here what we'll do is, we'll assume the initial level to be 0. Okay, h1 is equal to 0. Then this height we calculated already using trigonometry. It was 4 by 5 meters. No? So h2 becomes 4 by 5 meters. We'll use these heights in the expression for gravitational potential energy. Okay. So initial potential energy, since we assumed initial height is 0, initial potential energy will be 0. Kinetic energy, we need to calculate its speed, we don't know. So half m u square. Next, final potential energy. Finally, the bob is at a height of 4 by 5 meters. Okay. So m g h plus final kinetic energy 0. After reaching that height, the bob stops. Okay, so final kinetic energy becomes 0. That's all. Now 4 into 10, 40 by 5. This becomes 30. Right hand side becomes 32. Left hand side becomes 2u square. So you again get 2u square is 32. So u square is 16, u is 4 meters per second. So irrespective of which method you use, if the method is valid, you will get the same answer. We used work kinetic energy theorem, we got 4 meters per second. We use a mechanical energy conservation also, we get 4 meters per second. Okay, let's try another question. One last question of this kind, string bob. Fine. Again, let's say there's a fixed nail and a string is connected to that nail. And let's say an object is connected at the other end. Mass of the object is 2 kg. Length of the string is 5 meters. Now we release it from this position. Let's say it is released from rest. Initial velocity is 0. It starts swinging. Now at some instant, the bob or the string, not the bob, the string will make an angle of, let's say 53 degrees with the vertical, or shall we take 37? We'll take 37. At some instant, it will come to this position. When it is at this position, making an angle 37 degrees with the vertical, find out the tension in the string. Think of the steps first. The question now is to calculate tension in the string at this instant. Can any of you tell me an idea how can tension be derived?
So tension equal to mg cos theta.
So you are saying tension will balance the weight component in the radially outward direction. Okay, you have considered the forces. Obviously, tension is a force, so you have to think of some equation which helps you calculate force. Mg acts this way. Based on the angle made by the string, Mg will have a component in this direction. Mg cos theta, if you call this angle as theta. But Vanilla, why should they be balanced? Or others also, if you have any ideas, you can share. How can we calculate tension at that position? Or if any of you can tell me why they will not be balanced. Actually they are not balanced. Okay, tension is not equal to mg cos theta. Why? See, in laws of motion, we learned some ways to look at a situation. Okay, like one thing we learned was non-inertial frame and pseudo force. Okay, if you are observing from non-inertial frames, you have to apply pseudo force. Here we are not observing from a non-inertial frame. We are looking at it from the ground frame itself. That's fine. One more thing we learned in laws of motion is if an object follows a curved path. Can one of you recollect and tell me how we should analyze the situation if an object follows a curved path? What should we think in terms of? See, these are some common and very basic mistakes that students make. Okay, if object follows a curved path, always think in terms of tangential and radial directions. And especially if it's a part of a circle, think in terms of tangential and centripetal forces. Okay, and when an object is moving in a curved path, there must be a net non-zero force acting towards the center. Centripetal force is compulsory, tangential may or may not be there. In this case, actually tangential is also there, mg sine theta. That other component of mg increases the speed of the block as it comes down. We know, like from everyday experience, as the block comes down, its speed will increase, means some tangential force, tangential acceleration should be there. That is given by mg sine theta, which is immaterial for us as of now. Okay, but see, tension acts in the radial direction. Mg cos theta also acts in the radial direction. One is radially inward, the other is radially outward. You should write an equation for centripetal force now. Why? That's the only way you can bring tension into the equation. This is the direction towards the center. So centripetal force now will be T minus mg cos theta. And what is the basic formula for centripetal force? Anyone? Vanilla, don't answer. Others? Formula for centripetal force.
mv square by r square.
Correct. mv square by r. Our aim now is to calculate tension. To calculate tension, you need to know mass of the block given, gravity is known, angle is given. Radius we know, that's the length of the string itself, 5 meters. You need to calculate the speed of the block at that position. If you do that, you can tell the tension. And how will you calculate speed? You know initial speed is 0, and you need speed at this position. An object is moving, we know speed at one place and we need speed at another place. You have to think of which of these methods is applicable. There are 3 different ways to calculate speed in such cases. And you know equations of kinematics are not applicable, the other 2. One of the other 2 you can use. So solve this carefully, all of you. I'll give you 2 minutes or 3 minutes you take. By applying work energy theorem or mechanical energy conservation, first find out the speed of the block at this position. Okay, I'm erasing this tangential force, that's not necessary now. Find out the speed at this position. Once you know the speed, you can write you can substitute it in the equation for centripetal force and calculate tension. Okay, do this quickly. Yeah, Saket, good evening. We just solved one problem before this and we are now discussing this question.
Yes, sir. Thank you.
The block is released from position A at rest. When it comes to position B, at which the string makes an angle 37 degrees with the vertical, find out the tension in the string. That's the question. Okay. Yusuf, how are you trying to solve this? No reply. Okay. Rishi?
Sir, I'm solving, sir. 1 second. I'm almost.
Okay, okay. Make it fast. You have to calculate the tension. Okay. Let us discuss. Rishi, like which method are you using to calculate the speed? Work energy theorem or mechanical energy conservation?
Mechanical energy conservation, sir.
Fine. So see, as the bob or block swings from A to B, the forces acting on it are weight and tension. Tension does not do any work. Weight is a conservative force. Even if it does work, mechanical energy will remain conserved. So it's okay. And how do we apply mechanical energy conservation? Initial potential energy plus kinetic energy is equal to final potential energy plus kinetic energy. Okay. The conservative force involved here is weight, gravity. So the potential energy you need to consider is gravitational potential energy, mgh. So you have to know, I mean, yeah, you have to assign an initial height and a final height. It's your choice. You can call any one level as zero height. Okay. The equation will be correct anyway. So let's call the initial level as zero level. Nothing wrong in that. If you take this height as zero, okay, since it's the initial height, we'll call it h1 is zero. Then this final height, since it is below the initial level, the final height will be negative. And how much is this? Can one of you tell me this height? How far below the initial position is the block now? Simple trigonometry will give you that height. You look for a right angle triangle in this diagram and apply trigonometry, you can get that height. Rishi, have you calculated that?
I'm doing it, sir. 1 second.
Okay. Fine, listen all of you. It will be 4 meters. This is the right angle triangle which you can make use of. Okay, we know the hypotenuse, it is 5 meters long. Angle is 37, we need the adjacent side. So 5 cos 37, this will be 4 meters. Okay, the block is descending by 4 meters. So its final height, h2, should be taken minus 4 meters. Okay, so that these height values will help us in writing potential energy. So initial potential energy, since we assumed initial height to be 0, initial potential energy will be 0. And the block was released from rest there, so initial kinetic energy is also 0. Finally, when it descends by a height 4 meters, final potential energy becomes mg minus h you will have to take, so minus 4. And kinetic energy, half m, mass is 2 kg, v square. That's all. 20 force is 80. These tools will get cancelled. So we get v square is equal to 80. And you don't have to calculate exact v value. V square is sufficient for us. We will now take this v square value and substitute in the formula for centripetal force. That's all. Therefore, tension T, which is unknown, minus mg cos theta is equal to m v square by r. That's all. You will get tension from there. But let's discuss the idea once again. Calculation you will be able to do. So you are given a situation where an object is moving and you are asked to calculate tension. Tension basically is a force. If you want to calculate force, the only equation you can use is F net equal to ma, Newton's second law. In this case, tension is a force acting in the centripetal direction. The object is moving in a curved path. Whenever an object moves in a curved path, you should automatically start thinking in terms of tangential and centripetal forces directions. Okay, and you will see that tension is acting in the radial direction, means centripetal. So in the equation for centripetal force, tension will be present. Okay, so that equation is what we wrote here. But the formula for centripetal force is mv square by r. So to calculate tension, you first had to calculate the speed of the block. For that, we used other ideas. Like here, I solved it using mechanical energy conservation. You could have done it using work energy theorem also. You would have gotten the same answer. Any doubts in this? Okay. Fine. We'll come back to these, or shall we start now itself? Yeah, we can start now itself. No? Like I was about to say, we'll come back to these string and block problems later, but we can do it now itself. Let's see. Motion in a vertical circle. Very important part of the chapter. Usually, if they want to ask energy conservation based problems, usually they'll ask from this itself. Of course, other concepts are there, but more frequently you get questions from this. Consider a situation like this. Again, same fixed nail object and all. Assume an object is suspended by means of a string from that nail. String is an ideal string. Can one of you tell me the properties of an ideal string? Okay. Ideal strings are inextensible, massless. Means they don't stretch and their mass is negligible. Fine. Assume a bob is connected to the end of the string. Now, if we leave it like this, it will stay like this because tension and mg will balance. That's fine. Now, as we discussed in one of the questions today itself, if you strike the bob and give it some velocity, okay, at the bottommost position, you give it some velocity. Can one of you tell me what will happen?
Or it will go towards whichever side the velocity is being applied, force is being applied, and then oscillate.
And then,
And then after a point, it will stop.
no, wait, it will start moving in whichever direction we give the velocity. After that, what did you say? It was not audible.
And then it oscillates.
It will oscillate, you're saying. Okay. And what makes it stop? Like in a real life situation, we know if you disturb that stone or bob, whatever it is, it will swing for some time and stop. Why will it stop?
Due to air resistance, sir.
Due to air resistance, correct. Okay. See, we have given some velocity to the bob. Means we have given some kinetic energy, some mechanical energy has been given to it. Now, if it finally stops in a real life situation, we know the system will swing for some time and stop. Means the mechanical energy is being lost. So some non-conservative force must have been involved in a real life situation, that is air resistance. In an ideal situation, if you ignore air resistance and you ignore friction at the nail, then the bob will keep swinging forever. Because there's nothing to remove its mechanical energy. Gravity is a conservative force, tension won't do any work. Okay, so it will keep swinging forever. Okay, so if you give it a small velocity, it can go forward to some distance, or it can swing forward a little bit like this and come back, and it will keep swinging back and forth. That is what happens if you give it a little bit of velocity. Okay. Suppose you give more velocity to the object. Okay, more velocity than this. So second case, let's consider it like this. Some extra velocity has been given. Then what will happen? Like what will be the difference between this case and the previous case? Anyone? Saket, can you tell if you give some extra velocity compared to what was given in that yellow case? Wait, in that yellow, like first case, the bob swings still here on either side. Okay, it doesn't go beyond that point. So if you give it some extra velocity, what is going to happen?
Sir, it will form a bigger arc.
Okay, correct. It will swing to a greater extent. So maybe somewhat like this. So give it some additional velocity, it will go to some additional angle. It will swing with a greater amplitude, you can say. Anyway, let's not use the word amplitude now itself. You'll learn in a later chapter. Okay. You give it some more velocity, a little more. You can make it swing all the way to the horizontal position. You can make it go to this point. And it will stop there and come back. Comes back along this arc. You can call it circular path also. Arc is a part of a circle. And it will swing to the same height on the other side because its mechanical energy is conserved. This is what will happen. These are the different cases possible with increasing speeds. Okay. What if you give a little more velocity than this? The third case, it's able to swing to the horizontal position and come back. What if you gave it some more velocity when it is at the bottommost position? Pawan, what will happen?
Extra distance cover చేస్తుంది.
It will go to a greater height, some height greater than the horizontal position. Okay. Let's assume it swings. All the way till here. Okay, it has crossed the horizontal position, so it will start moving to the left after it crosses that point. Because the horizontal position is the rightmost position. After that, it will start curving. The path will start curving to the left. Somewhat like this. So maybe it reaches till here. But see, this is the tricky part. After reaching that height, okay, once it crosses the horizontal position, no, the object cannot come to rest. Anywhere at these positions, okay, in the bottom half of the circle, the object can come to rest. But once it enters into the upper half, the object cannot stop. We'll discuss all that, why it cannot stop and all. But see, like now you got a picture of what happens as you give greater and greater velocities. Okay, we know that as an object rises, its speed decreases. Okay, these ideas are very important. Concentrate, all of you. As the object rises, its speed decreases. Okay, decreases, that's fine. What makes speed decrease in this case? The component of gravity opposite to velocity. It gives negative tangential acceleration. That's why the speed decreases. Now you imagine speed decreasing in the lower half. You consider that yellow case. Okay, like first case. As the speed decreases, at some point the speed can become zero because mg component will always be there in the tangentially opposite direction. So it stops. But after stopping, the bob cannot fall down because the string is there. It is tied to the string and the string's length cannot increase. So it cannot fall down. It will have to come back along the circular path. So it swings. Same in the green and orange cases also. But once it crosses that horizontal position and goes up, okay, let's assume it stops. We'll prove later that it cannot stop in the upper half of the circle, but let's assume it stops. Even if it stops, the problem there is that it will have to fall like this. It cannot come back along the circle. Okay, why won't it come back along the circle? Because string cannot push it to the right side. String can pull it into the circle. It cannot push it to the right. If the velocity becomes zero here, due to gravity, it will have a tendency to fall down. But to come along the circle, to move along the circle, it will have to go outwards like this. Who will push it to the right side afterwards? String cannot push, string can only pull. Okay. So basically what happens, once the bob crosses the horizontal level, the same horizontal level as the nail, once it crosses that, there's a chance that it falls into the circle. Okay. But if you give sufficient speed at the bottommost position, if enough speed is given at the bottommost position, let's take this fifth case, it can even complete the entire circle and keep going round and round. So situation would become somewhat like this. You can achieve this also. Okay, so with one particular velocity and any velocity beyond that, you can make it complete the entire circle. Okay, just a moment, I'll show you one image, you'll understand better. Okay, consider this Hot Wheels track, all of you. The diagram is not high resolution, but I think you get the picture. So basically what happens here is, what is present here is a loop track for the car to move. Okay, it's a vertical loop, vertical circle actually. We are looking at it from an angle, so it doesn't look like a perfect circle, but it's a circle when you see properly from the side. So it's, the hoop is somewhat like this, right? There it is in blue, here it is in orange. You can make out the difference. So it's like this. So basically what happens is the car, the toy car, should enter into the hoop from here. It should move along the hoop, complete the vertical circle, and leave from here. Fine. Now, from everyday experience, you can tell, if you give the car only a small speed before it enters into the hoop, one of you tell me what will happen. Like suppose the
it'll go to
car,
us.
wait. Suppose the car is released from this position. It will only gain a little bit of velocity because only small descent is there. Rishi, continue. What will happen?
Sir, it'll only go towards, like, cover some distance and then come back.
It can only rise to a small height on that hoop and it will come back. It will swing. Okay, in this case, swinging is not possible. It will rise up to a certain height and go back along the track. Okay. Suppose you release it from a slightly higher position. What was the second color we used? Green and then orange. Okay. Suppose you release the car from this position. Since you are releasing it from a slightly higher position, it will enter the hoop with a slightly greater speed, but there's no guarantee that it will complete the circle. So what will happen? It may go to a certain distance and then slide back. Okay, in that second diagram also you can visualize. It will rise to a certain height and slide back along the track itself. It becomes too slow as it rises. It won't be able to complete the circle. So you go on increasing the speed. In one case, maybe when you release from here, you will be able to make the car go exactly to the horizontal position. Okay, means exactly the lower half will be covered by it. So it rises up to that point, but then its velocity becomes too less. It will swing back. Okay, it will go back. Fine. Now you give it velocity just a little bit more than that. Just a little bit more than required to clear the horizontal position. This is the interesting case. Here what happens is the car enters into the loop. It rises to a certain height. It crosses the horizontal position, but it becomes too slow. There you will see it falling off into the track like this. Okay, it won't be able to go all the way to the top. But going all the way to the top is also possible if you give it sufficient velocity. So if you release it from the necessary height, you can make it complete the loop along the track itself and go out of the track like this. Okay, so this is what effectively we are discussing. Now in this case, in this particular track and car case, it's the normal force from the track which helps the car rotate. In the case that we started discussing, it's the tension in the string which helps the bob rotate. Okay, like the equations will be similar. Here, you'll write equations in terms of tension. In case of an object rolling on a track or moving on a track, you'll write equations in terms of normal force. Okay, now what do we have to find out in this? First, you should be able to tell how much speed the bob should be given to reach a particular height. You should be able to calculate calculate that. Then you should also be able to tell how much speed needs to be given to complete a circle and keep moving along the circle without falling into it. Okay, so these are the things that we need to do. Fine. We'll start with one Very important derivation. You all only have to do it actually. Just a moment. So from the bottommost position, okay, let me copy this. Let's say the bob is not released, the bob is pushed such that it gets a velocity u. Okay. Let the length be L. Assume it is known. Let the speed here at the bottommost position be u. Remember, whatever we are deriving is in terms of speed at the bottommost position, but we'll solve some problems with speed at other positions also. Okay. Now, as it swings, at some random instant, let its speed be v, which is unknown. You can calculate v if you are given this angle. That's what we did in the 3 questions that we solved today. And if you can calculate the speed in terms of the angle, you can tell the tension in the string in terms of those values. Okay, do this all of you. Length of the string is known. If you want, you can take mass as m. It will get, okay, yeah, in tension you will have mass. So length is known, mass is known, speed at the bottommost position is known, and the angle of rotation is also known. So L, M, U, and theta. Of course, G is known, acceleration due to gravity. Derive an expression for speed at that position. And after that, we'll write the centripetal force equation and get the expression for tension at that position. Okay, but first do the speed part, all of you. What are the different methods that can be used to derive the speed? We know speed at the bottommost position and we need speed at some other position. What are the different methods that can be used?
Sir, same one as the previous question.
You can tell the methods, no?
Uh,
Okay. Huh.
Work done total is equal to delta Ke.
Work energy theorem or mechanical energy conservation. One of them can be used. Okay. Do it, all of you. Derive an expression for speed when it rotates by an angle theta. Use mechanical energy conservation. Okay. Saket, any expression for speed?
Yes, sir. 5h final plus u square.
Keep G as G itself. And H final you can express in terms of L and theta. Like H final is not given to you, no? So that should not be there in the expression. Anyway, Pawan, any answer for speed?
U square minus 2gl bracket 1 minus cos theta is equal
U
to v
square
square.
minus 2gl into 1 minus cos theta is equal to V square.
Yes.
Is this okay? We'll see. We'll see. I think this is correct only. I'll tell you one more shortcut also to find out speeds in such cases. Listen, we are trying to apply, or we are applying mechanical energy conservation. And the potential energy you need to consider in cases like this is gravitational potential energy, for which we need to assign heights first. Let's assume the initial height is 0, initial level is 0 height. Then the final level, if you see, again, trigonometry, you see a right angle triangle forming here. We know the length of the string is L. So this part is L. Then this height, which height? This part becomes L cos theta. Then the remaining height, the actual height by which the bob ascends, will be L minus L cos theta. So the final height should be taken as that value. H2 is equal to L minus L cos theta. You can write L into 1 minus cos theta. So initial height is 0, H1. Final height is L into 1 minus cos theta. Is this part clear to all of you? Any doubt in this? Okay. Then since initial height is 0, initial potential energy becomes 0. Kinetic energy is half mu square. Final potential energy will be mg into that height, L into 1 minus cos theta. Final kinetic energy half mv square. We don't know if it has stopped or not, but we are deriving an expression for v in terms of theta. That's all. As I said, for speed, the mass won't matter. And cross multiply with 2 or multiply throughout with 2. You get u square is equal to 2gl into 1 minus cos theta plus v square. Therefore, v square is equal to u square minus 2gl into 1 minus cos theta. This is correct. Okay. We got an expression for v square. From that, you can get v also. That's fine. Now, one of you tell me how to derive the expression for tension at that point or at that level. We need an expression for tension in the string at that angle. How to derive that?
T minus mg cos theta equal to mv square velocity.
That's all. Centripetal force equation. T, tension will be acting along the length of the string. Mg acts downwards. There will be a component of mg acting this way, radially outward. Cos theta, because if that angle with the vertical is theta, this angle will also be theta. So T is acting towards the center, mg cos theta is acting away from the center. Net force towards the center will then be T minus mg cos theta, and you equate that to mv square by r. R in this case is L. Okay. Therefore, T becomes mg cos theta plus mv square by L. I'll write it as m by L into, in place of v square, we'll substitute all this. Okay. So u square minus 2gl into 1 minus cos theta. So this becomes mg cos theta plus first term mu square by L minus m will get multiplied, it becomes 2 mgl divided by L, that L will get cancelled. 2 mg into 1 minus cos theta. We can simplify this further. mg cos theta plus mu square by L minus 2 mg plus 2 mg cos theta. Minus of minus becomes plus. Therefore, tension in terms of theta or tension at an angle theta will be, first we'll write this mu square by L term plus, how many mg cos theta are there? 3 mg cos theta minus 2 mg. So with this you can tell the tension in the string at any angle. Okay, we applied energy conservation to derive V square first, and after deriving V square, we are using the centripetal force formula to get an expression for tension. Now, observe this equation for tension. U is the speed with which the object is projected from the bottommost position. Okay. Mg is a constant, weight of the object. As the bob moves along the circular path, theta is the variable. From point to point, in this equation, theta is the only variable. So we got tension in terms of one variable theta. Fine. And observe very carefully, theta is the angle made by the string with the downward vertical. This direction is called the downward vertical direction. Theta is the angle between the string and that downward direction. Okay. At the bottommost position, tell me, when the bob is at the bottommost position or when the string is at the bottommost position, how much is theta? When the string is at the bottom. Rishi, what were you saying?
That only.
0. Okay. And cos 0 is 1. That's the maximum value of cos theta. So at bottommost position, tension is mu square by L plus 3 mg cos 0. Cos 0 is 1 minus 2 mg. So effectively tension is mu square by L plus mg. That's the tension at the bottommost position. You can tell that without using this equation also. At the bottommost position, tension acts upwards, mg acts downwards. So you can directly say T minus mg is mv square by r. So it becomes T minus mg is equal to mu square by L. You get T is mu square by L plus mg. Same thing. Okay. So for the bottommost position, theta is 0. I'll write it in brackets here. Right. Now as the bob swings, theta increases. One of you tell me, as theta increases from 0, starting from 0, what happens to cos theta? We know cos 0 is 1. As the angle increases, what happens to cos value?
Decreases, sir.
Decreases. Cos 0 is 1. Cos 90 degrees is 0. Cos 180 degrees is minus 1. So it keeps on decreasing up to 180 degrees. Okay. And in this case, in the situation that we are discussing, 180 degrees is the point where the bob is at the highest position in the circle. Okay, topmost position of the circle, rough diagram. Okay, that means as the bob rises, tension keeps on decreasing. That is what the equation suggests. Because the other terms in this tension equation are fixed. Mu square by L depends on the speed with which you project it. 2 mg is the weight of the object. Mg is the weight of the object. So these two are fixed. This is the variable term. In that part also, cos theta is the variable term. At the bottommost position, cos theta is highest, so tension is highest. As the bob swings away from the bottommost position, theta increases, cos theta decreases, tension decreases. So keep this point in mind. I'll mention it here. As the bob swings away from the bottommost position, theta increases. That means cos theta decreases, and that means tension decreases. Okay. Next class, we will make use of this idea to derive some more things about this situation. And we will also prove why the object cannot come to rest anywhere in the upper half of the circle. Okay. And we will derive how much speed is needed for it to go to the top of the circle and complete that loop. And in all this, we are using mechanical energy conservation. That is why this is part of this chapter. Okay, fine. Let's quickly go through what we discussed today. So first we solved some problems where you are given the speed of the bob at one position, you are asked its speed at another position, or maybe tension at another position. Okay, then we started discussing motion in a vertical circle. We first visualized what happens when you give different amounts of velocity at the bottommost position. We took an example of this Hot Wheels track. Then we are now deriving the equations. If you know the speed with which the object is moving at the bottommost position, then you can tell the speed at any other position. And the idea we used here is mechanical energy conservation. We derived an expression for V square. Using that, we derived an expression for tension. This is very useful. Okay, thank you all. We'll continue on Friday. Friday is 11th, no? Yeah. Mostly I'll be taking in the same time, 6:30 to 8. Okay.
Thank you, sir.